Okay, and welcome back everybody to TezAsia Hackathon 2022. Today we will be going through the Legos and for the fundamentals of Lego with Dealer here. So please welcome Dealer from Marigo. He will be walking you through what the fundamentals on Lego is. Thank you.
So, thank you and welcome. So my name is Didier Plando, and I'm going to present you Lego and mainly all the stuff which are behind the language. So what is Lego? Which is mainly it's a programming language for writing Tezos smart contracts. So the dedicated target is Tezos. So why Lego first? Because we know that we have different languages, and the first one, which is Michelson. So Michelson suitable for application developer. Then you can write applications like Michelson, but if you go through the code, you have to define some types. This is quite natural, but you have to write code, and code is based on what we call a stack machine, a stack-based machine. So you have to think about pushing information, popping, and so on. And it's not really natural for all the developer. So for this purpose, we decided that Michelson is not very suitable mainly for application developers. So the goal here is to reduce the barrier of entry and also in order to minimize risk of bugs. For example, in Michelson, we already have some types and so on, but we are going to see what kind of optimization and so on we are going to see in Lego. And the solution is to define high-level language, and the target to compile for the compilation is to target Michelson as I would say the assembly language, because this one is directly executed and by the Michelson virtual machine. And one key point in LIGO provides different syntaxes in order to cater different developer tastes. In order to, for example, if people were JavaScript, they can take the JavaScript style. If they prefer OCaml ones, they take the OCaml style, and so on and so on. So first, we are going through the LIGO foundation, what LIGO is in general, and then after we will go deeper in one syntax. So first, syntaxes. So LIGO offers 4 syntaxes, and each syntax is as close as possible to the language it is inspired from. So for example, the first one, which has been Pascal LIGO, which has been, of course, inspired by Pascal. And this one provides what we call an imperative developer experience. Imperative means we describe the operation in sequence of instruction in order to change the program state, okay? This is quite natural, and when we come from object-oriented programming languages and so on, the imperative style is mainly one of the most used, C, and so on and so on. The second one is Camel LIGO, and this one has been inspired by OCaml, Objective Camel, so we say OCaml right now. And this one offer and provide a functional style. Functional style and consider computation as an evolution of mathematical function based on composition and so on. So it's quite different because you don't have to think about sequence. You think about evaluation and composition of function. The third one, which is Reason LIGO, and Reason LIGO has been inspired by Reason ML and is really, really close to Camel LIGO. Same for Camel and Reason ML. You have the Camel LIGO and Reason ML and Reason LIGO. We don't really push Reason LIGO right now, and we prefer people to use Pascal LIGO, Camel LIGO, but also the last one, which is GS LIGO, which has been inspired by JavaScript and TypeScript also. In order to provide experience which is close to these languages, and this one also provides what we call an imperative developer experience, like Pascal LIGO. So we have two different, two kind of syntaxes. The first one, which is Pascal LIGO and GS LIGO for an imperative style, and the second one, which is Camel LIGO and Reason LIGO for a functional style. And here today we're going to see and just to go through the LIGO compiler and the capability of the language through the GS LIGO JavaScript inspired syntax. So GS LIGO. Uh, since LIGO can be source code can be written in Camel LIGO or Pascal LIGO or Reason LIGO or GS LIGO, we have a kind of interoperability. Interoperability means each code which is written in Camel LIGO can call code which is written in Pascal LIGO and vice versa, and the same for GS LIGO and the Camel LIGO and Pascal LIGO and so on. So here we are in the front end, we have different syntaxes, but at the end, each syntaxes in different files, you can merge different files with different syntaxes, and the compiler don't complain, and everything works well. So how does it work? First, this is a high level and coarse grain compiler overview. So just to show how it works and why we have this kind of property. The first one, which is the first layer, which is called the front end, which is the ability and capability to parse different syntaxes. So you have different parsers mainly. The first for Camel, the second for Reason, Pascal, and GSLIGO. Once the parsing has been done, the source code is parsed, and as a result, we have an intermediate representation of the code. So as you can see, Camel LIGO, Reason LIGO, Pascal LIGO, and GS LIGO are going to be how to say transform and transpose in this intermediate representation, which is unique, which is the same. Just to be sure, it's really a coarse grain overview. So here in the intermediate representation, we don't care about the syntax right now. We just have what we call abstract representation. The second stage, which is really important, is the type checker. So we have a type checking stage, and the type checking stage role is to take the intermediate representation and try to prove that we have good properties when we talk about types. And as a result, we have what we call a typed intermediate representation. And the last stage, which is the compilation to Michelson, and this compilation take the typed intermediate representation and produce the Michelson source code. Be aware, this is really a coarse grain. We have a lot of stages, but mainly we have two main stages, which is the three main stages: the parser, the type checker, and the compilation. The type checking is really important because it offers some properties, and one of the properties is soundness. Soundness means that when we use types, the types are mainly used correctly and so on, and the type checker is here to validate and to see if the code manipulates types as expected, of course. And the second one, which is the compilation to Michelson, is really important because this break offer and provides some properties related to performance. Performance means we are going to optimize the code in order to have the most optimized code, and optimized code means also less gas consumption. So this is a long job to be done because it's a day-to-day work, and the compilation, the contract of the compilation, the assertion of compilation is to offer a code which is how to say which don't consume gas, don't consume too much gas. And just for information, most of the top layers, which are the parsers and so on, the type checker is written in OCaml, which is just for internal overview. And the last stage is written in Coq. So in Coq, it means we have some properties and theorems based on, and the theorem states that compilation is optimized or not, is well optimized. And this is done during compilation. So this is just to show that performance are, how to say, properties which are proven. So right now we see the overview. So the foundation of LIGO, so with the compiler and so on, the different stage. So we are going through the GS LIGO overview. So first, GS LIGO is based on types, as mentioned, and one type because Michelson already records types. So these types should be, how to say, should be provided to Michelson. So these types are also provided in the LIGO layer, so in the LIGO language. And this is done in each syntax. So if you use Camel, you have to provide types, Reason ML, and so on and so on. So as mentioned, LIGO is a strongly and statically typed. Strongly, it means we cannot write function without, how to say, specifying the type. So you have to specify the types each time you have to write the function. And statically typed means that your types are checked during the compilation. They are not duck typing during the execution, like for example, Python and so on. And the role of the compiler is check. So during the type checker, of course, the compiler checks how the code processes data, so the manipulation itself, and at the end, it ensures that each function expectation are met. It means that once we want to use some function which manipulates integers, we cannot we can only apply the function on integer and nothing else. And this is one important feature. This is not really, this is quite natural if you go through some traditional languages like, I don't know, so OCaml, Haskell, Java, Swift, and blah, blah, blah. So we have first some native types. Native means basic, which is offered by the language, like integers. It's like integers can be negative or positive values. For example, minus 42 is an integer, and 42 is an integer also. We have naturals. Naturals means it's a 0 and upper. For example, in order to have a natural in GS-LIGO, you have to write one as nat, and the as nat mentioned to the compiler that one should be manipulated as a natural. Of course, if you write -1 as nat, the compilation is rejected, and the compiler refuses to take -1 because it's not a natural by essence. When you have to deal with variables, you have to use some specific function which is offered by the different libraries. So if x is an integer and you would like to have a nat, you have some features, some function which let you do some cast, some transfer from integer to nat, and so on and so on. We have strings, which are quite natural, like for hello from LIGO. Bytes, for example, with the 0x. And for example, café, which is in French, which is a well-formed byte. Of course, you have a lot of, here we have just some native types, and you have a lot of types which are offered also by the language. You have some types which are related to types manipulated directly by Tezos, like the like addresses, for example. You have also the Tez for the currency, the cryptocurrency, which are manipulated by contracts, because one important feature in contract is the gas. And if you want to execute, you have to pay the gas. So the cryptocurrency is used to pay the gas, but also to do some transaction. You also some types which are related to the new features or new topics which are offered by the protocols. For example, the chest, the tickets, the roll-up, and so on. And so on and so on. So if you want to dig and to learn the basic and native types, you can go through the LIGO documentation and check and see these types and how to manipulate these types and what kind of functionalities are linked to these types. Since we have native types, where we have what we call the complex or structured types. The first one, which is the tuples. Tuples, in fact, lets you gather different values in a specific order. For example, you can be pair, triplets, and so on. And the order is really important. And each value, each values which are gathered in these tuples are called components, and you can retrieve these values using their index. Since we have your order, you have the index, and the index start by 0. So, for example, we can create a point which is x and y, and now you have which are abscissa ordinate as you want. And this one could gather two integer, the first for the abscissa and the second for the ordinate. So this is the way we define the point type. So we use the keyword type, the name point, and then after the equal, you define your type with a square bracket for the tuples. This is the syntax for GS-LIGO. In CamelLIGO, it's parentheses and so on. So you have to check different syntaxes if you want to use CamelLIGO, PascalLIGO, and ReasonLIGO, sorry. Of course, you can write function. Here you write a smart constructor. So we can create a new point, and this new point is waiting for two variables. and we are going to create a point. And in order to create a point, you just have to create a pair, and using the same syntax as type with the square brackets, and then after you can gather the two parameters in order to create a point. And as you can see here, the function return the point type. And here the point is just an alias to the type, which is the pair of int and int. Here we can write square bracket int followed by another one. Here we write point just to have a semantic based function type, which is much more interesting. And of course, we can write extractors, accesses to different value, to different components. The first one, which is abscissa, which is at the index 0, and the second one, which is at the ordinate at the index 1. So here, as we can see, the pair don't let us define some semantic aspect to each integer. The fact that which is abscissa is just because it's the index 0. So we have to carefully manipulate this type. And here, since the types are the same one, which is two integers, it's not really readable. So this is why manipulating at points directly is much more easier and simplified, how to say, the code readability. We have what we call records. Records, in fact, it's data which gather, in fact, once again, different values, but each values is linked to a field. So you do this each in fact association field values are packed in a single type, and this single type is called a record. And the record is made of a set of fields, of course, and each field, as mentioned, has a name and a value. And value is given by a type. So a value is characterized by the type. So for instance, back to the point, we can define two new types. The first one, which is the coordinate, with abscissa and ordinate. And here the abscissa is an integer, ordinate is an integer. So if we compare with the first one, which is a tuple, here the coordinate is a record, and each integer is linked to a field, which offer much more, how to say, semantics once we read the type. So we know that the first one, which is the integer, the first one is the abscissa by definition, and not by the usage as we can see in this slide, because here in the index 0, it's abscissa because the function is called abscissa, nothing else. And here we define abscissa and ordinate by name. So we have the name too, which helps us to, how to say, to give much more semantics. Of course, we can define also another representation for a point, which is a polar representation with a radius, which is an integer, and an angle, with also an integer. So here we have two different records, and in order to summarize the idea here, we gather different values with fields which are linked for each value. So based on this, we can write right now a new smart constructor, which is the new coordinates. So here we are waiting for two integer, and we build, as we can see here, a new record with an abscissa, an ordinate, just describing the name, which are, how to say, specifying the type previously. And of course, if we would like to retrieve the abscissa, which we can try the extractor, which is a gate, or the projection if you want, which take a coordinate and produce an integer just using the dot notation. And then you can write c dot abscissa, and then after you have the integer related to abscissa. One important point here is here we manipulate, and once again we have the coordinate, which is a tape which has been defined here. Okay. And that's all. So you can define records. One important point in LIGO, which has never mentioned, is LIGO has no side effect capabilities at the top level. So you cannot define types with mutable values. For example, if you remember in Objective-Camel, you can use ref types or mutable records, mutable fields in records. Here in LIGO, this is not possible. You don't have these capabilities. You don't have the capability to mutate a record. So the only way to, to mutate a record is to build a new one. So this is why smart constructors are really useful, and let us write, how to say, safe and pure code without any mutation. This is really important. JS LIGO has no mutation capability at the top level, so you cannot write a coordinate with trying to modify the abscissa with a kind of affectation and so on. This is not possible. Um, and the last type, which is a variant. Variant is a type that is defined by different, how to say, constructors, which is what we call also algebraic data types. If we are aware of Haskell and OCaml and so on, of all the functional programming languages. And in fact, we define different cases for the variants. So for example, we can define the point right now, and the point can be a coordinate or a polar. And as we can see here, we have two kind of construction. The first one, which is called coordinate and is waiting for coordinate, which if we remind, the coordinate is the one which has been defined previously, which is the record here. And we can also define the point as a polar representation with the constructor polar and the internal representation, which is the polar type, which has been defined, as mentioned, also before in this slide. Okay. So here point can have two different aspects, two different values. The first one, the point could be either a coordinate or could be a polar representation. And then after, you have to deal with the code. You have to deal with these two different representation. But before, let me show you how to create a point, which could be, for example, a coordinate or polar. So once again, we can create two smart constructors. The first one, which is the point coordinate, which is waiting for C, which is a coordinate, the record, which is previously defined. And if we want to provide a point, we just have to call the function, which is coordinate, applied to C. And here coordinate is what we call a constructor. And the polar, for the same polar, we can create a point, which is a polar representation, thanks to the polar constructor. And here, one important thing is coordinate builds a point type, and polar also build a point type. So you have different aspects, and you have two different capabilities to build the point based on coordinate or polar. And this let us mixed different records, but behind a single type, which is a point. So if we can create different values for the same types, we should have an operation which let us do the deconstruction of this type of the point in order to see if it's a coordinate or a polar. So mainly most in the languages we have, say, for example, if we deal with an type, we have what we call the switch case, the switch table construction. So here in GS LIGO, we have the same one, which is called case matching. And case matching lets you recognize and deconstruct the data in order to retrieve the internal value. So in order to do this, we have a special function in GS LIGO. It's quite different for example, in Camel LIGO or Reason LIGO and Pascal LIGO. But in GS LIGO is given by this simple construction, which is match. Match takes a first parameter, which is the data you would like to deconstruct and recognize and deconstruct. Here, P is a point, and P could be a coordinate or a polar. And for each constructor name, you have to give a function which describes the behavior which should be executed once the data has been recognized. For instance, here we can define a function which is a predicate, which let us to see if the point is coordinate or not. So I don't know if it's really important, obvious, but let's write this function. This function take a point and return a boolean. And once we do a match of P, once we decide and we see that it's a coordinate, we are going to execute the function. We take a C and return true. So here we define the function. And if it's a polar, we execute the polar the function which take p as a polar type and return false. So the match, this is the unique and the only way to do the pattern matching and the deconstruction in GS LIGO. And this one is really important because there's one important property which is offered by the match and which is verified by the compiler, which is the exhaustiveness. Exhaustiveness means if you write the match, but if you omit to specify the polar entry, the coordinate, the match is going to be rejected by the compiler because the compiler is going to complain and saying that the pattern matching is not exhaustive. So this property is really important and show that it offers some soundness and some good properties in order to write good contracts and how to say with strong properties like safety. Safety, as you know, that once you originate a contract, you cannot modify it. So the safety is one important feature and property which should be offered by the language. And this one should be done during the compilation. So exhaustiveness is done during the compilation. So once you do and you manipulate variants, exhaustiveness is checked every time, and this property is not fitful. Fitful. The compilation is rejected. It's also important because you can decide during the implementation, you can decide to extend, for example, your variant, adding a new representation. I don't care, for example, I would like to use another representation. I don't care. Introducing the time, I don't know. I don't care. And if you recompile the code, the compiler is going to complain because some code and some portion of your code should be revisited because you have to offer the behavior for the new construction. So as you can see, this property is important for the compilation. During the compilation, during the lifetime, once you decide to say review and provide a new contract based on a given one, and this property show you the what is missing and so on during the compilation. And for instance, also if you decide to remove if you remove one representation, the compiler is going to complain because you have some entries where we are going not to recognize because it does not exist anymore. So pattern matching is really important, and we are going to see why. Is how to say it's fundamental. It's really a foundation and fundamental in GS LIGO and other syntaxes also. As mentioned before, GS LIGO and Pascal LIGO also some imperative style. Imperative style means we have constant and variables. So I just mentioned before that we don't have some mutation, but I mentioned this in top level. You can have some mutation, but in some blocks and given function. So with a local scope. So for instance, we have a constant. So if you take care, all the code which has been written before, for example, function has been introduced with the const keyword. So each function is a constant, is defined as a constant. And here, for example, we define a function in constant function which is called x, and take a as an integer, and return something. A is not used here. Is used. This code is really stupid, but this is important. Here we define the constant age and return it. And the constant means we cannot modify it. At the opposite, we have some what we call variables, which are introduced by the let keywords. And here we define let c to be a, and here we can see some another property, which is we have to define types for function, but sometimes once we define the variables and so on, maybe you don't have to provide the type because the compilers can infer the types locally. Here we see that a is an integer, so c should be an integer also. So you don't have to specify the integer for c. And then after, the second statement is we modify C adding B, and then after we return C. So we just here we're just redefining add with local variable definition and local mutation. and the scope of mutation cannot be outside. Okay, so if we return C, we return the value of C, not the variable C. This is important. It's not like C or C++ and so on with the pointer. Here we return a value. So we have the let and the const. So here it is just the capability to have some modification based on the let keywords. So if we have the let keywords, we can also have some iteration with imperative style, and this one are introduced with the loop and imperative style. So for example, we can define a function which take a list. So here it has been defined with a generic type with a list of int here in this part with the parameter which is linked to the value L. And then after we are going to return an int. In order to do this, we are going to introduce first a variable which is called total, which is an integer we define with 0. Here, the integer can be removed, of course. And then after we have a kind of for, not a for comprehension, but a for loop construction, which take, how to say, a binding, uh, uh, which is I, and each value of L is bind to I. And then after we can modify the value, which is total, or the variable, adding I each time we go through each time we visit the list named L. And then after we can return the total. And this is what we do when we would like to do some loop in the imperative style. We can do also the loop with a functional style, but if you do it, LIGO requires some, I don't know if the slide, so no. If you do it in the functional side with a recursion, for example, you have to carefully provide a function which is called tail recursive function. It means that we should offer a function with a good property, which, how to say, don't bring or don't let the code raise, for example, Stack Overflow, something like this. And writing function with a tail recursive is not really easy sometimes. It could be really hard. It could be done automatically, but it's really hard. So you have to provide it by hand. So this is why in GS LIGO, we prefer to use the imperative styles for the loops and so on. It's much more easier and how to say, is much more canonical in GS LIGO. So we see the different data types, which are the native types, the tuples, the recalls, the variants. We see how we can write some function. We see that how we can loop and so on. And all this code at this type can be packed and can be organized, what we call modules. Or namespace in GS LIGO. So we use both words. Module is high level and much more generic because modules cover each syntaxes, and namespace target the GS LIGO syntax. So namespace let us define some types. So here we define the type T, which is a natural. We define an addition. We take two variables, A and B. This is the old syntax. We takes two variables, and A should be a T, a natural. B should be a T, so it's a natural. And then after we provide the addition. We provide 0 and 1 as a basic constant, 0 for 0, of course. And here we see that 0 should be managed as a natural by the compiler. So we mentioned this with a asnat construction, and when with the asnat construction also. So these types and these three functions are packed in the namespace. So the namespace let us organize the code by how to say, you have what we call a semantic. So I have a question. Is that similar to object like in JavaScript? Yes, it looks like object. Object is an instance. Namespace is the specification, right? So you have a specification. You don't have to instantiate. The object is an instantiation. The object should be compared to the record, and the record you cannot embed types in the record. Here in the module you can embed function values So constant like 0, 1, and the add for a function, but also the type. And this is really important. This is why namespace is different to object, as you mentioned to in JavaScript, Mantas. So here we have a semantic approach, and here we can define a namespace which is a currency, which is a euro, and we can decide that T is we are going to manipulate euro. How we can use it? You can use an import, so we can use a euro as a module, and here we link the module with the name, the keyword euro, and then after we can define a contract which is going to manipulate, for example, some euro, and here the type storage is defined using the type T, which is provided by the namespace euro. Okay, so we see that the namespace offers types and functions and values. And then after, we can define a returns types, which is a pair with a list operation. I don't care about operation. This is a Tezos native type, and a storage, which has been defined just before. And then after, we can define a main function. We take an action, which is a unit, and the storage and returns returns. And here we can see that we can use the types in order to define the storage type, but also we can define, sorry, a function which increment, which add one to your, for example, to your storage, using the euro add function, the add function which is provided by euro namespace. And in order to do it, you have to provide a type T which is provided by euro, and one is as this type. So everything is okay, and the type checker is quite happy and don't complains. So here we can see that we can use types, function, and values which are bring and which are offered by the modules. Okay, so types are really modules packed types and definitions like function or values. So this is really important. So I have 20 minutes. Okay. And as we can see here, we have a special record, so, which is a dash import. And here we can write a euro .js LIGO. This one could be written in thanks to Camel LIGO or Pascal LIGO or Reason LIGO. And once you import it, you can use it in your files. Even this one is written in JS LIGO. Okay, so the interoperability here is used and is done thanks to the import, and the compiler can use it seamlessly and don't complain. Is able to how to say, to import the file and compile it directly thanks to the abstract representation as mentioned during the LIGO Foundation presentation, and just after the parsing and the first stage and the first representation, which is the abstract one. So here we can see that we can use different source file of LIGO and different tastes on different syntaxes. So the modules are really useful if you want to organize the code and so on. One important feature is also is a file define implicitly a namespace. So for example, you can define this one, for example, the file we are looking here. And if we call this file main.jsligo, we can import it. And once we import this file, we have to link it to a name. And this brings a kind of namespace view. So the file is a kind of namespace unit also. And this one is bring and let's say express thanks to the import keyword. We also have another one which is the include. When include is much more like the CPP, C++, the C preprocessor include, and you replace the include by the code. So there's nothing related to the namespace and so on. So we prefer to use the dash import because dash import lets you organize and to also to provide some namespace capabilities around the code which is imported. For example, you can define different types, and one approach is to define types which is called T. For example, in OKML we define T, but the T is offered by the module or namespace, so we can retrieve it based on the namespace.t and so on. And this with this operation, we can differentiate a T which is offered by the namespace on another one. So based on this and saying this, we can go through what is a contract. So first we have to deal with what we call the anatomy. A contract has a given shape. So the first one is a storage. So the contract received a value, and this value came of the storage. And the storage is the value which is manipulated and archived by the Tezos blockchain once your contract or transaction has been validated by the blockchain. So first, the storage came from the blockchain and is offered. You have what we call the parameter. Parameters is the operation we would like to do once we call the contract. And here, as we can see, the parameter could be done and could be, how to say, defined thanks to a variant. So this is what variant types are really important. And here we define two parameters, which are increment and decrement with an embedded value, which is an integer. Each parameter and storage have to produce, once we have a contract, the contracts have to produce some operation or transaction, which should be validated by the blockchain. And the result should be, the type of the result should be a list of operation, which should be empty, and the storage. And finally, the behavior of the contract, take an input as an input, which is a pair, which is a tuple, which is a pair of a given parameter we call an action, and the store which has the type storage. So here we have an action which has type parameter, the store which has the type storage, as we can see as an input, and the output should be the result, which should be also a pair with a list of operation and the storage. Okay, so basically the contract takes a storage parameter and have to produce as a result a new storage with some operation which should be validated. So here we can write a main function, and this main function take, as mentioned, the first pair with the storage and the parameter. The second one should be the result. And if we would like to write the behavior itself, we are going to write a match action. So we are going to recognize and deconstruct the variant type with increment and decrement. And once we recognize the increment, we are going to execute the function which takes n as an integer, is going to increment the storage, the store, which is an integer. So we're going to produce a new one. Same for decrement, we're going to remove n. So we are going to decrement storage. And this match operation is going to provide an integer, which is the right type as a storage, and we're going to return an empty list as a list of operation. Okay, so here we mention and we have to say give some information to the compiler like types, and we mention to the compiler that this empty list should be at a list operation. So it's going to check and to see if the as list operation is correct. It's not a cast, it's just a type annotation. Okay, it's not a cast. This is really important. So here we can see that we bring everything. We have the pair, we have the variant type, and here, based on what we call the behavior, we see that we have the loop with the storage. We see offer to the behavior, and the behavior should offer new storage. And this manipulation of the storage, if you remember, I mentioned you that the parameters, the storage cannot be modified. We have no mutation. So here, this loop really highlights the fact that the storage is offered to the behavior, and the behavior should offer a new one. So you have to offer a new storage by construction. You have no mutation. Okay, nothing is done behind the scene, and this one is really clear with the mechanism which are offered also by Michelson, since the storage should be archived and stored only when the transaction is accepted. Okay, this is really important. So we're going to see, we have to see here, we see the what is the contract. And one important, how to say, property is the capability to test the contract. If you are not able to test the contract, you are not able to see if the contract works well and so on. So testing the contract is really important, since the origination could be done once and no more. Okay. So testing is done and is offered thanks to testing what we call a framework, and we have a testing framework in LIGO. And this testing framework lets you write the test in LIGO itself, and it works directly with the LIGO code. So of course you can try to use Tezos and so on and so on. And in LIGO also offer a specific and dedicated library which is written also in LIGO. So you can reuse the code and so on in the test. And the test is the LIGO code. So all the properties which are offered for the local compiler are also applied to the LIGO the LIGO test. And this one is this LIGO frameworks offer extra types in order to provide some types, and also let us manipulate Tezos context. So you can manipulate some Tezos variables like chest and so on, addresses and so on. So based on this testing framework, you can write what we call unit tests. So if you're already aware of testing, you can write unit tests. The unit tests are quite simple. It's just to call one function and to see a function return the required expected value. You can also write end-to-end test, what we call integration test. Integration test means you are going to execute a contract based on doing the origination of the contract, executing the contract, and see how the storage has been, the changes done, and once you do on the contract, how the storage is changed during the contract execution, not during, but just after, before and after. So you can write what we call end-to-end test. You can also write what we call mutation testing. Mutation testing capability to take a test, some test, execute this test, but the mutation is going to mutate some operation and see if some, how to say, if the code is covered. So if he let us to see if all the code is covered or not. For example, if you do some test to test, for example, the increment, not the decrement, mutation testing is going to perform some, how to say, transformation in the add, and is going to see that the mutation and the decrement is not called. So then after mutation testing, say, okay, you do some test, but this one is not done. So if you call the test with a decrement, it does not work because this one is not test. Okay, this is the behavior and the main goal of the mutation testing. We have also, this is one new feature which is coming. We have what we call the random generation of random values. And this one is very important if you want to do some property-based testing, as known as PBT. So the property-based testing is capability to call the test with a bunch of values. So we can generate and ask the generator to generate random values and to call the test. So here it's the capability to random values at the limit. For example, the max value for the integer, 0, and so on. Some negative one, positive one, and so on, and to see if the code and the behavior is the right one. Okay. So, for example, if you try to call, I don't know. A function to see if this function works fine with negative values and so on. And this is the target with PBT. This is a brand new one and it's going to be available soon. We have the first merge requests have been requested and accepted, but we still have some work to offer a library dedicated to PBT. So the last capability is the capability to catch error during transaction. As you know, Michelson virtual machine offers a specific function which is a fail with. Fail with capability to stop immediately a contract once, for example, some properties are not verified. For example, once we call a contract, we can try to see the parameters and we to see, for example, if the increment is using the right value or not. If it's not the case, we're going to abort the code as soon as possible. Why this one is really important? Because if you try to execute some code and this code is not, how to say, the right one, we are going to spend gas for nothing. So the fail with is really important in order to fail with immediately. And so the capability to check the fail with is also offered by the test framework. So you're also able to see if the fail with are correctly raised, and if you are able to catch the expected exception. If you don't, if you offer, for example, some parameters with how to say, unexpected value, something like this. Okay, and this one is covered by the code and should be done in and should be programmed in your contract. So it should be provided and should be also verified in the test. So the test lets you try to catch error during transaction. So and this is just a simple example of end-to-end testing. We are going to not going to through the unit testing and so on, but just this one, and just to show you how to write a end-to-end test with the origination and so on. For example, we would like to test the increment, so we are going to create a function which is should increment, which should return a boolean. So the first two operations, I'm going to create an initial storage v42 as int. I mentioned it's an integer. Okay, this is useless for the compiler, but I can do it. I'm going to do some test origination, calling a specific function which is offered by the testing framework, which is offered by the namespace, which is called test. So we are going to call test.originate. And in the origination, take the contract. I see if you remember, the contract, the first contract could be stored in the contract file, as mentioned in the import file here. So we're going to take the function main, if we remind the namespace. So we are going to use the main function offered by the contract, and we are going to how to say apply the originate on the main function, the storage, and the initial balance of your contract. Then after, as a result, we have a triplet, and the first value of the triplet is the address. And if we have the address, we can once again, thanks to the test namespace, retrieve the contract, which is the contract we are going to use in order to execute it. So the address is strongly typed, and we have the contract to contract, and then after we retrieve the contract. Then after, thanks once again to the test module, we are able to execute the test to contract exception. And here we are going to execute increment one with the contract which has been already originate, and we give one meters and for the transaction. And as a result, we have the gas consumption. So we have the value and the number of gas which has been consumed during this execution, thanks to the Michelson virtual machine, which is used for by the testing framework. And then after, we can do the assert, which should be this one. We are going to retrieve the storage thanks to the address, which is the new storage, which has been produced during the execution of the contract and during the execution of incremented by one. And we should verify that the storage at the address should be the initial storage plus one. Okay, so here we can see we just find line of codes. We create a storage, we originate the contract, we retrieve the contract, we execute the contract, and we checked the storage. Quite simple. And the last line is just for the testing framework. Everything which is started by test underscore is executing, as I said, directly by the test framework. And that's all. You have an end-to-end test. So just to finish, LIGO is a language with a front end and so on. It's a compiler, but in order to increase the adoption of LIGO, we offer different kind of materials. The first one, which is a LIGO catalog, and the LIGO catalog, in fact, is a different set of libraries which are stored in a LIGO long GitHub. But this one is going also to provide we are going to provide it thanks to the ligolib.org website. And we explain and we offered how to say contract, but also the web client also, which uses this contract. And this contract covers gaming, NFT, random generators, big array, and so on, and so on and so on. We have a lot of contracts which are defined, and this contract can be how to say you can use this contract, and we are going to see how to use it. So this one are going to be provided by the ligolib.org, but you can also go to the ligolib GitHub directory and see how this contract works and so on and so on. And we have also documentation. We have ligolib tools, of course. The first one is the CLI. The CLI lets us to compile contracts. Of course, the compilation means all the stages which has been explained in the first slides, which are the type checker and so on. You can also express the expression compilation. This one is really important because if you want to do some origination, you can construct a LIGO expression and compile it to the Michelson one. Okay, so then after, once you have the Michelson value, you can create, you can originate, thanks to the Tezos CLI, the contract compile contract, which is the Michelson source code, and the compile expression, which is also the Michelson value. So these two compilation facilities let you compile the contract and expression. You can run tests, of course, because we have the test framework. You can do some dry run, so you expect some values and you do some dry run. You have what we call the package manager, thanks to Easy. So once you build a library in LIGO, you can you can package this library and publish it thanks to Easy command. And this command is provided by the CLI. So for package manager, this aspect offers the capability to push a new library, but also to use the library in your project, as we can do, for example, for with npm and package.json, if you use JavaScript code, or Maven or Gradle and so on. This is the same behaviors with the CLI. So you have to define also package.json to JSON description if you want to reuse libraries. Sorry. And the last one, which is the brand new one, which has been, which is going to be published today with the last version, and I think it's going to the version 42 or 43. I don't remember. I don't know if it's 43 or 40 or 42 or 43. I have to check. This is a scaffolding. A scaffolding lets us use the contracts which has been how to say offered in GitHub, which are mentioned just before the catalog library, and the scaffolding in this case create initiate a new project, create a brand new one, taking the code and doing a GitHub a kind of Git clone, and create a brand new project, and then after you can use it, and you have a 0-day usage. You can use it immediately. Okay. So this is a scaffolding, and the scaffolding is really a brand new one. The scaffolding CLI, you can retrieve it with, for example, Angular CLI and so on. You can create French brand new one projects and so on. So it offers capability to reuse projects which are offered by the LIGO Lang. Building code means also tools to write code, so IDE. So we have the web IDE, which is available under the website, which is ide.ligolang.org. So this one is the current one, but we are going to have a brand new IDE, and this coming soon also. It's a matter of days, to be honest. It's just a matter of days, or 1 week or 2 weeks at least. So the new one is much more, looks like much more VS Code. And this one is going to be provided and is going to replace the web IDE. And you will have all the possibilities, the compilation of a contract expression, but also you can do some test execution, dry run, evaluation, and so on and so on. You have all the capabilities of CLI, which is going to be offered by the web IDE. You have also the VS Code, so you have the capability to edit and implement your contract thanks to VS Code. So we have a LSP plugin. So you have kind of compilation which is done on the fly, and you have feedback during your experience with VS Code. You have also, of course, the syntax correlation and so on. This one is offered for the fourth of syntaxes. Of course, once we have errors, some errors are raised directly in the VS Code. And since we have VS Code capability, we have the Git pod. So we can use also, so for example, once we do some workshop, a 3 hours duration workshop, we use Git pod, and Git pod offers you the full capability of VS Code. And as we can see here in the left side, we have the file view. with VS Code 1, which is quite standard. And at the right side, you have the Per, which is the editor, and you have the terminal, so you can access the terminal. Because all the capabilities are bring and how to say offered by a Docker, which is automatically deployed thanks to Gitpod. Of course, if you want to use a roots editor, you can use VI or Vim, but also Emacs, so you have some nice features like syntax correlation and so on. If you want to learn LIGO directly, you have what we call tutorials, and the tutorials is offered thanks to a given website, which is academy.ligolang.org. So you can access these tutorials, and you can learn LIGO, and so you have different aspects, and you can learn step by step JS LIGO or Camel LIGO, Reason LIGO, or Pascal LIGO as you want. And this slide is the last one, and this is what I would like to share with you. And I hope it helps you to understand what LIGO is, how it works, what is the foundation, the fundamental properties of the LIGO, sorry, and also everything which is linked to the ecosystem, like the tools, like the libraries, the contracts, and so on and so on. So thank you for that for this presentation. And if you have any question, I'm ready to ask and to answer to this question. Is LIGO developed by Tezos? LIGO is developed by LIGO. So LIGO is a company. Think you have two different companies. You have Smart Chain, not Smart Chain, sorry. Smart Chain is one company we are working with. You have Marigold and you have LIGO. And Marigold is a kind of umbrella, but LIGO, we have a dedicated team, developer, we have a core team, which is around 10 developers. And LIGO is developed thanks to the grants offered by Tezos to the LIGO company. And the second one is the namespace, but I already give the answer related to the namespace, the difference between objects and namespace. And one important feature is the namespace to say in-bit types, but also behaviors or values. So this is what's called a namespace. It's not a record. So I don't see no more question right now.
Yeah. Okay, I don't see any questions well. So perhaps we can end it off here if there's no more questions and there's nothing else. So I would like to thank you, Attila, for actually for presenting on LIGO, and have a nice day. Yeah, we will still have, for the rest of the participants here, we will still have the workshops tomorrow, and if I'm not wrong, the last workshop will be either on Sunday or Monday. So yeah, thank you everyone for your time and your questions. See you again.
And thank you. Bye bye.
Thank you. Bye bye.
Bye bye.